Hello everyone, welcome to 3Dnatives' latest webinar, How to Choose Your AM Engineering Grade Material and 3D Printer. My name is Madeline Pryor. I will be the moderator for today. I will introduce my, actually just hello panelists as well, welcome.
Hi Maddie. Hello.
Hello.
So I will introduce myself and the panelists in a little bit, but just before we started, I would like to share with you all a poll which will be appearing on your screen right now. Please answer the questions. It's just to learn a little bit more about you and also about your expectations for the webinar. I'll leave it up for a few moments to give you a chance to fill it in. Also, as people continue to trickle in bit by bit, it's just 4 now, so I don't think most people will be on time. But yes, welcome again. Just for your information, we will be recording this webinar today, and you will be able to find it on the 3Dnatives YouTube channel, probably by the end of the week, if you would like to rewatch it, or if you want to share with your friends or anything else. Anyone who is just coming in, there are a few of you, don't forget to answer the questions that are currently on your screen. As I said before, they're just to get to know a bit more about the attendees of the webinar, as well as to understand your expectations for today. So, yes, have quite a few people answering. I also want to remind everyone that there is a dedicated Q&A bar should be on the bottom of your screen. You can ask questions throughout the presentation, and there's a dedicated time at the end for questions and answers. I will be choosing among the questions that I see in the Q&A, so do add something if you have a question. There should be an option to just send to the panelists or to everyone if you want. You can also ask questions anonymously if you would prefer. I will not be asking any of you to go on the screen, so don't be shy. Ask any questions that come to your mind. And yeah, so I think we have a lot of people answering. Maybe I'll just give it another minute for any of the stragglers to answer the question. And yeah, okay. I think that's the majority of you right now. So I'm going to end the poll. You should now be able to see the poll results. It seems that most of you are currently working in the field of additive manufacturing, which is very interesting. You seem to have, it seems to be tied between people who are other or have their own 3D printer, and many of you seem to be using FFF FDM, which is good because that is the material that is what we'll be focusing on today. And for those of you, the 48, who want to know about AM in the materials field, don't worry, we will be covering that. Okay, so if we could just move to the next slide. I am just going to present the webinar itself so you know what to expect. The first 10 minutes are going to be the introduction done by 3Dnatives, which is myself. We will then be moving into the sector that talks about the requirements and the applications of engineering grade materials. Finally, we will be presenting 3Dgents' new printer, the Industry F350, they will be talking about its specs as well as how it can be effectively used for printing engineering grade materials. And then, as I said before, there will be a Q&A session in the last 15 minutes. Please ignore the timing. It should be to 5 CET for those of you joining from other areas. All the timing are in Central European time. And yeah, please ask any questions you have. We will make sure to go through with them, and we'll talk about it during the Q&A section. Okay, so moving to the next slide. Today, we will be discussing, as you know, engineering grade material, how to choose it, and what the requirements are from your printer to create the best quality part with these materials. 3D printing is now used in a variety of markets, as you can see on the screen, notably in the aerospace and defense, healthcare, automotive, consumer goods, and construction sectors, among others. Increasingly over the past few years, we have also seen a movement away from using 3D printing solely as a rapid prototyping tool into actually having it being used to create end-use parts. This has been seen especially in the aerospace, healthcare, and automotive industries. If you look on the slide, you'll see that in aerospace, healthcare, and automotive, they do use engineering grade materials, which are what's required to make things like final use parts. In terms of moving into this, in aerospace, we have recently seen that 3D printed parts have made their way onto lunar landers, satellites, rockets. In medicine, 3D printing is used for a variety of applications, though you might most commonly know it for prosthetics and implants that are customized to a patient's need. And in the automotive industry, we're using 3D printing as a way to make lighter, more efficient parts for vehicles, as well as allowing for greater customization, especially in luxury vehicles. As you can imagine, as we're moving into creating end-use parts and not just using it for rapid prototyping, the materials used in additive manufacturing are becoming increasingly important. The materials we'll be talking about today, engineering grade materials, are not the materials you would use on your desktop 3D printer to design small decorative parts. They are parts that are being created with additive manufacturing rather than subtractive manufacturing, where we're seeing the movement away from traditional methods into additive manufacturing. So as a result, the parts themselves need to be strong and effective. If we could just move to the next slide as well, as you can see here, material choice is very important in AM, and having said that, it makes sense that it's grown immensely in the past few years. According to data from Senval, the number of 3D material suppliers have doubled from 2017 to 2019. And of those material suppliers, the market is really dominated by polymers and thermoplastics, what we would commonly refer to as engineering grade materials, among a few other things. There are different, of these, one of the most common are polyamide, PA products, especially, which are part of the thermoplastics market. There are different grades, PA6, PA11, and PA12, though PA12 is by far the most common. If you look at the graph on the screen, you'll see that there has been an immense increase in materials from 2017 to 2020. And now let's move on to our panel. As I previously stated, my name is Madeline Pryor. Welcome to everyone. I am the English content specialist for 3Dnatives, the largest international online media platform on 3D printing, which is available in 4 languages, English, of course, but also French, German, and Spanish. I will be the moderator of this panel and of the Q&A. I would again like to remind you to ask any questions in the dedicated Q&A section, which will then be answered later on. Now to introduce you to your panelists, apologies in advance for any mistakes on names. Filip Tujicki is the R&D manager and head of applications at 3Dgents. Filip has over 7 years of experience in the additive manufacturing industry. He has worked with printers using a variety of different 3D printing technologies. Based on this experience, he's an expert in material science and 3D printing technology applications. Maciej Sidorowicz is the marketing director at 3Dgents, the manufacturer of industrial high-performance 3D printers. Maciej has over 7 years of experience in creating 3D printing solutions that drives customer improvements in production line performance and prototyping capabilities. And last but certainly not least, Krzysztof Roguski, is the R&D manager at 3Dgents America. With 6 years of experience in the additive manufacturing industry, Krzysztof built the 3Dgents America R&D core team, which works on the development of 3D printing ecosystem solutions. Welcome, gentlemen.
Hello, everyone. Hello, and thank you for introducing us.
Hello, thank you for the introduction.
We can now move into the discussion itself. Go ahead.
Thank you, Maddie, for this introduction.
Again, I want to say hello to everyone that's attending today. I hope you are all in a good health. As Mehdi already explained, we are all coming from a company called 3Dgens. For the past 7 years, we are manufacturing industrial grade 3D printers. You can find our solution on Navy vessels, in atomic power plants, and of course in aerospace industry and automotive. During those years, we managed to achieve some kind of information, especially about high performance and engineering grade materials that we want to share today. I strongly believe that what you will learn today will be useful for you in the future, and it will help you to choose the right material for you and the right 3D printer. So not to prolong our introductions, let us start with the actual content of the webinar. And Philip, our material specialist, will start with the material segmentation.
Okay, hello everyone. I think it's a great opportunity to take a deeper dive into, well, engineering materials, but actually we will start from trying and demystifying the pyramid of materials. I'm fairly sure you have all seen it before. This is no news to anyone probably, but let's try and really figure out what it means. So maybe let's start with how the pyramid is actually divided, because it's split in two different ways. One division is almost purely driven by a physical property of the material, and that would be the separation to amorphous materials and semi-crystalline materials. And okay, just a very brief focus on each. Amorphous materials are, in very broad terms and in very general terms, materials that are unable to create an orderly structure within its own mass. You would call this structure a crystallite or a crystal, but a characteristic of semi-crystalline materials or crystalline materials is the ability to create those structures, and it strongly affects the properties of the material itself. Nylon, for instance, is a engineering grade semi-crystalline material that strongly affects its properties, its rigidity, its elongation, its tensile strength, while amorphous materials, where, for instance, polycarbonate is an engineering grade material, that is amorphous, and it's actually unable to create those orderly structures in its mass. This is important because it actually creates specific necessity that the printer has to accomplish to actually be able to use those materials to the best possible outcome, basically, wherein the outcome is actually, the performance, the mechanical performance of the part, the dimensional stability of the part manufacturing. So this is just a slight introduction, really, to the demands that the printer has to cover, in essence, to allow for good use of those materials. Okay, and the other separation in this pyramid is actually, you could almost say, cost in respect to performance. And you can also get away with calling it a performance separation. So starting from the top, those are your high performance materials. And those are really, the kings amongst materials. Those are materials that are almost capable of, they have great mechanical properties. They have, great chemical resistance, great thermal resistance. You could say they're jack of all trades, almost. So for instance, one of such materials is polyether amide, commonly called PEI or Alten. And that's actually an amorphous material. And while simultaneously you have PEEK, which is also considered a high performance material, but it's a semi-crystalline material. And getting one stage lower, we have engineering materials. This is actually the main topic for today. And those are materials that have a very strong focus on one specific feature, which they excel at. And so they are a very good balance between performance and cost effectiveness. So those materials are really the materials that are driving the applications. You could go as far as saying that those are the paramounts of industrial application and use. And then on the bottom of the pyramid, you have what we here call prototype polymers, but you can also call them commodity plastics. So these are, great all-rounders, but those are very basic, cost-effective materials. Okay, let's carry on to the other slide.
There is one thing we should also mention here. We specifically taken out the ABS from the prototype polymers and we've placed it in the advanced engineering polymers. We will explain why we did that, why we did this. There is one very strong factor that's very important to that, but I believe Philip will cover that on the other slides.
On the later slide, exactly right. Okay, and since the topic for today is actually engineering plastics, we are focusing on the middle layer of the material pyramid. So the materials that are specifically chosen for a distinguishing feature and that are also cost effective in their applications. Such materials like polycarbonate or polyamide, and ABS for that matter, as Mateusz has mentioned, are materials that have a very specific feature that might make them very applicable in specific regions of industry. We'll cover that in a little more detail at a later slide, but we can basically distinguish them as being very targeted materials. So you could say that there's a very wide variety of uses for those specific materials, and every material really fits the bill for some specific application. And that's really what is important when it comes to choosing a printer that is capable of using both amorphous and crystalline engineering materials, because it has a very specific demand. Every material will call for something slightly different. So models printed with engineering grade materials, depending on the material we have opted to use, are capable of being, functional prototypes, for instance, because they might have, like polyamide, a very good wear resistance, and it would make for a very good functional prototype of a mechanical device, for instance. You could say that they have enhanced mechanical properties in that those materials in general perform better on mechanical tests than commodity plastics or just prototype polymers like PLA, for instance. There is also a very interesting and developing, which is a great thing actually, movement for optimizing for 3D printing process, and this group, engineering plastics, is benefiting very strongly from this. So you can, we are now starting to see, more materials being engineered or compounded to fit 3D printing process better, and especially with materials like polyamide or polycarbonate, for instance. It just make them, more applicable to the 3D printing landscape in general. Also worth mentioning, there is a multitude of different grades of those materials. Just considering polyamide, there are really a lot of different grades. Like the three that we're mentioning here, like PA6, PA12, or PACF is just the tip of the iceberg. There's polyamide 666, 669, 618. It's literally pick and mix sometimes. And it's all driven by the application in the end. and those materials can also be rather easily modified because they are so widespread in the industry. There are a lot of different compounds with different blends of those materials almost readily available. They might not be perfectly suitable for the 3D printing process right now, but as the optimization of those materials goes on, those materials become more and more applicable. Okay, let's continue. Okay, now let's focus a little bit more on three materials that we have chosen. And now actually we will explain why we chose ABS as an engineering material. And I have a print here that I think could sum this up fairly nicely. It's a very large geometry. It's actually a part of an enclosure. And this part will only fit its application in its intended use if it's manufactured to simulate well the actual material that it will be used, that it will be made from in the final design. Of course, the manufacturer of this specific equipment will manufacture it by injection molding, but at the prototyping stage, at the lifetime testing, at the user experience design, they want to simulate the material as well as it's really possible. And you have so many different grades of ABS that you can literally have tens of degrees in processing temperature differences. Well, we all know that even desktop printers are capable of using ABS, but really what it boils down to is those are such a wildly different grades of materials that when we're talking about industrial applications of ABS, we are really referring to a commonly used engineering material. And so with the higher grade of ABS materials, which actually requires a heated chamber to prevent warping and deformation, it requires a slightly elevated nozzle temperature, usually revolving around 250 degrees. This actually becomes really important. That's why we've made the choice to actually incorporate ABS in this section. Okay, polycarbonate, a very different material, excellent for impact properties, but also demanding when it comes to good processing. Again, a lot of different grades exist. There is a characteristic of the material that is called glass transition temperature. And without getting into too much detail, you could say that this is a temperature at which the material loses its ability to exert a deformative force and basically build up internal stress. And so to properly manufacture parts from polycarbonate, you could start at 117 degrees for some grades, all the way up to 140 degrees to match this, this requirement. And only then you can actually reap the full benefit of printing a polycarbonate part. And this is actually what makes printing large pieces from polycarbonate possible. This is how it feeds to the design of the printer and the actual choices behind a 3D printer equipped to make good use of those materials. And finally, polyamide, also an interesting material, but for slightly different reasons. It has different stiffness, it has different rigidity, it is a very tough material. It is also a semi-crystalline material, which is in fact also important for how the printer is actually using it. And with this regard, it's actually important how the printing profile or the guideline of how to work with the material is considered, as well as sourcing the material itself. Also, polyamide is actually great for wear-resistant functional prototypes and actually final products as well. All of those materials can be compounded to have a very specific use. One of those modifications is electrostatic dissipative. Those materials modified in this way actually have the ability to dissipate static charges, which makes the part safer for handling electronic components, for instance. Another one, also very interesting, is flame retardation. And here, another aspect of the 3D printer comes into play. Flame retardant substances are mostly bromide based chemicals, and they can be harmful if not filtered out. As such, the printer should be equipped to deal with this problem. And carbon fiber and glass fiber reinforcement is, of course, an option. Okay, carrying on with the applications. And since I covered this in quite some detail, I will go very briefly through those possible applications. Of course, you can create fit and form test parts. This is just to see if the intended shape or user experience design is okay. It's just basically a fit and shape check, basically. Functional prototypes, of course. You can create parts that will be able to deliver useful information from the function of the part that you have created before you actually commit to other manufacturing methods. Casings, it's also a brilliant application, especially if we consider ESD materials for housing electronics, or polycarbonate for impact resistant enclosures. End parts, as Maddie has already mentioned in the beginning, this is beginning to grow significantly. If the engineering material is chosen well, and the part itself is designed to be well printed, or well printable, you could say, this can actually lead to a functional end-use part. And finally, jigs and fixtures. Just to name one methodology that reaps huge benefits from this is 5S methodology. Calling for customizable jigs and fixtures for almost anything on the factory floor. Okay, and a very interesting case that I will try to summarize. An automotive industry manufacturer has been presented with a task of preparing themselves to manufacture a new type of engine. They had limited access to the parts on which to base their assembly process. This company has employed engineering grade material 3D printing, ABS and polycarbonate, to print the elements before they could actually get the real part and create the whole assembly line, the whole assembly plan. Basically go down to production optimization, all based on 3D printed parts. So when the actual shipment of parts has reached their door, they welcomed it, well prepared for the task. And this actually allowed them for weeks in time reduction, and basically yielded great results when it comes to application for engineering grade materials.
Thank you, Philip. Right now we'll go to Krzysztof that will describe the first case study that we received from our American part of the business.
So the second application that, okay,
yeah, Maddie?
Apologies, I just wanted to tell you we have about 5 minutes left in this section, and also to remind everyone to ask questions if you have them in the Q&A part. Thank you.
Thank you.
Thank you. So the second application that we want to present is actually replacing metal on demand. So the customer has the part which we're manufacturing before in the metal, and thanks to changing the process to 3D printing with advanced engineering materials, they were able to save not only $600 on this application, but also cut the lead time from 2 weeks to 65 hours. at the beginning, they choose the industrial grade ABS for the fit and form, and they check this. They were able to produce these parts with the functional threading to assemble this and check on the production line. And after that, they produce the final part in polycarbonate with carbon fiber reinforcement, which right now serve really good on the production floor. You can go to the next slide. So to print objects, as Philip described with the materials, there are some technical requirements for the machine as well to be able to create the parts with the mechanical properties desired for these materials. One of the things is the dual extruder modules. Then you can use the dedicated support solutions, which will not only save you time on the support removal, but also enable more complex geometries and the wider adoption of the technology. The quick ability to change between the print heads and between the modules will allow you to have wider range of the materials within one printer. There are different settings and different requirements to processing ABS and, for example, polycarbonate or pick and pack materials. To wrap it up, all of this information is the automatic process control, which will take you from the slicing software through the printer, which optimize loading temperatures and all the sensors inside the printer controlling your environment during the printing. The industrial grade extrusion system, when we are going to printing with materials like carbon fiber, reinforced polycarbonate, we need to make sure that our extrusion system will be able to handle those challenging materials. And the heated chamber. Philip mentioned about different grades of the ABS. If we want to have the greatest, the best mechanical properties of our ABS, we need to have dedicated heated enclosed chamber, which will go to 80 Celsius, for example. This goes with enclosed heated chamber. We have the industrial air filtration, as this is more and more studies right now coming about the safety of using the 3D printers. An industrial filtration system will assure you there will be no fumes going out from the printer. And the dedicated side chamber for the materials handling and surfaces for materials like, for example, polycarbonate. Can go to the next slide. Some key enablers of the shifting from the rapid prototyping to the rapid productions are dual head modules. They are far more beyond the complex geometries and the design freedom, but it's also about the throughput and productivity within one machine. You don't want your high-end engineers removing the support from the models. You want this to be labor-free process. And the one important thing about printing with dedicated support solutions is the dimension stability of the model, especially surfaces which are supported. As an example of the complex geometry, which is the lattice structure, that's a great example of the weight reduction with the same mechanical properties, which will be not possible to be printed without the dedicated advanced support solutions. As you can see, we use here the carbon fiber PEEK material, and you can see the part printed with support. On the next slide, we have the same lattice structure. After 1.5 hours of the support removal, no touch support removal, you can see that there is no residue and there is no material left. That's far also the complex geometry, but also the surface finish. There is no chance that you will scratch this model during removing support. And also when you print more complex geometries with the fragile segments and fragile parts, there is no chance that the part will be damaged during the support removal process. To take this to the next step, we created the CT scan of the lattice structure that we printed without dedicated support and with the dedicated support. What you can see right now is the scan of the CT scan of the lattice structure, which was compared with the actual CAD design. And you can see the majority of the colors are within 0.5 millimeters deviation, which is not acceptable for the engineering applications. And you can see heavily distortions on the bottom surfaces. On the next slide, we have the lattice structure printed with the advanced support solutions, which was removed in 1.5 hours. And after that, we've made one more time the CT scan. The majority of the model is green, which indicated 0.1 millimeters deviation, from the desired dimension. And also when we go through the lattice structure, you can see that there is no distortion under the support surface. Okay. The second key enabler for the shifting from the rapid prototyping to rapid production is the fully enclosed heated chamber. That will assure us that we will be having the best mechanical properties out of our materials. That will assure the dimension stability in every part of our printer, and that will assure the repeatability of the printed parts. During the current pandemic, we saw the disruptive manufacturing when we need to produce the parts on demand in the different parts of the world. And sometimes the printer is in the very hot environment. Sometimes the printer is located in a very cold environment. And with the fully enclosed heated chamber, we have this assurance that the parts produced in the different part of the world will have the same dimension stability. And this connected with the industrial filtration system will give us the safety that there will be no fumes, especially with printing with ABS materials or fire retardant materials. Okay. And the very important topic is preparing the material for the printing and also maintaining the material during the printing process. So side heated chamber, when we store our material during the printing process, especially during shifting to from rapid prototyping to rapid production, the prints are getting longer, and we want to make sure that our part will have the material printed in the same environment. So it's beyond the visual quality. As you can see on the left, that's the material which was not dried and not prepared correctly. And on the right, we have the material which was maintained through all the printing process correctly. It is beyond the visual quality. It's also about the mechanical properties and dimension stability of the printed object.
Okay, so right now we are finishing this part where we tried to answer the question how you should choose your engineering grade material and what are the requirements for the printer that you will use after that. My job right now will be to sum up and I will try to guide everyone through some questions that you may ask at different steps of the process of choosing the printer and the material. What Philip already said at the beginning about the materials, every one of them has some specific features that you may want to use. So the first question you should answer is, what are the exact requirements for my application? Is there a working temperature that should be achieved? Is there a dimensional stability that I will need to achieve with the material that I want to choose? After answering those questions, you should be able to narrow down the possibilities of materials that you will use. The next one is what we also mentioned. Are there any special features? By special features, we mean do I need an extra stiffness of the material? So I need carbon fibers. Do I need a flame retardancy from the material? Should it dissipate electric charges? These are also very important questions that you should ask at the beginning of your process when you are still choosing the material that you will use. Then there is a research part of your job. So you should go and find the material you need, and you need to find the manufacturer of the material that you will use. When you are going through this process, you definitely should take closer look on the stability of the manufacturer of the material. So we are talking about maintaining quality with different material batches, about the dimensional accuracy of the filament you want to buy. So all of those questions will help you to choose the right material for you. And I'm hoping that at the end you will choose a material that will be perfect for your application, and you can start looking for a 3D printer that will allow you to print and to achieve all those great features that were mentioned before. When we were talking about the materials, we said that some of them need 120 Celsius degrees in heated chamber. Some of them, if you are focusing on accuracy, needs soluble support. All of that features are very important, but you should not forget about ease of use of the solution that you want to buy. So auto calibration, very low need for maintenance is also a good thing for a 3D printer. And please do not forget about the safety of your operators. Hazardous fumes, so advanced filtration system, locked chamber, so no one will place his hand into the heated chamber when you have 120 degrees inside. That's quite hot. At the end, I believe past year showed us that being flexible is important, especially when you are managing various projects in the industry. We've seen many broken supply chains and many problems that occurs during past 12 months. So we are also strongly recommending to look at the possibility to upgrade the system that you are considering or changing only a little bit in it to achieve other results. Our final advice, ask for sample. The sample will tell you about the quality of the print, about the dimensional stability. You can check the mechanical properties of the part. All of that should help you to choose the right 3D printer for your job. Right now, I will finish the part about materials and printers. I'm sure that we only scratched the surface, but we are hoping that you will be able to ask the right questions right now, and you will receive an answer that will satisfy you. And we will go to the very exciting for us part of this presentation, because this is a first sneak peek of the peak word is fancy right now because it's also considered as a material. So we wanted to show you our new industrial 3D printer, the 3Dgens Industry F350. So of course, I'm sure that you can see that the printer is standing behind us. We want to speak only a little bit about it because the official launch of the printer will take place on the 1st of March, and only after this date you will be able to get all the information. But right now, at the beginning, I said that we gathered some experience through past 7 years. And we used this experience to create a 3D printer that will fulfill the needs of engineers on the manufacturing floors, that will fulfill the need for creating jigs and fixtures from engineering grade materials in the mechanical properties that you will expect from those materials. So all of the features that Krzysztof mentioned before are implemented into our newest solution. As you can see, this 3D printer is equipped with everything you may need, even industrial grade extrusion system that will allow you to print with composite materials without excessive wear. This is truly important right now because this part of the business of 3D printing business is growing, and the composite materials are more and more important right now. Just a very short sum up about what our solution that we are introducing for you right now can do. 340 by 350 millimeters of build volume. This is quite large, especially when we are considering 130 Celsius degrees in heated chamber. This is a temperature that will fully allow you to use engineering grade materials. This is the temperature that's needed to take the stress out of the material that's being printed. So you can be sure that the part you are taking from the printer is in the specification that you are thinking of. So the dimensional accuracy, the mechanical properties, everything is in place. Of course, hot and temperature, 500 degrees, far more than enough for most of the materials that we are using. The most temperature-driven material right now that we have in the portfolio is PEEK, but this is still enough to process this material. And of course, we cannot stress it enough that the new materials and the material science is the thing that's pushing forward the AM industry. So we want to focus on the materials that will have those features that we talked before. So flame retardant materials, ESD materials, even PEEK with carbon fibers. These are the materials that are game changers right now. You can use high performance materials as a substitution to the metal parts. And one of those materials, I believe, requires a special mention. Right now we are working with Victrex to introduce the AM200 PIAC material to our portfolio. This is also something what Philip mentioned, that many manufacturers of the filaments right now are taking much closer look into optimizing their materials for 3D printing. Because at the end of the day, the functional print for the user is a good machine and a good material that will work perfectly as a duo in this solution. Okay, Mehdi, I believe we taken out the required time, the time that we had for this webinar. I'm hoping that we covered a lot of topics. I'm sure that there are many fantastic questions that right now we can wait on an answer.
Great, thank you so much. That was very interesting. I hope you all thought so too. So thank you for your questions. You can continue to send questions if you have any. We have the next 15 minutes dedicated to question and answering. We'll get to as many as we can. So first question is from an anonymous attendee, and it is, what could you do if the printer is not equipped with features that allow for proper printing conditions?
Philip?
Okay,
I believe material science is your part.
Okay, yeah, I will take that. It's a great question that has really been asked for years now, and it has driven the market, the material market, to try and deliver versions of the materials that are free, or at least display less problems due to the printer itself not having the features required. So let's take a desktop device without an enclosed chamber, no heated environment. Okay, some parameters are deal breakers. If your nozzle can't go high enough to actually process the material, you can't really do anything about that. But if chamber temperature is considered, which is really a big factor, and it has an enormous impact on the characteristics of the product that you will end up having. So, for instance, there are versions of polycarbonate material that are, well, they're not warp free in room temperature processing, but they will display less problems while being processed. One notable example would be Polymaker PC. It has a fairly low glass transition temperature. It's a great all-rounder, and you could just source your material with your limitations in mind. Those materials are really out there, but please remember, there is a payoff. You will pay in mechanical performance because those materials are very specifically compounded, and there are engineering grade alternatives which will, well, truth be told, blow other variants of those materials out of the water when it comes to material, parameters or mechanical parameters compared. So just keep this in mind, and to a specific degree, you can actually get away with printing ABS, but do not expect stellar results when it comes to mechanical properties. It's just not physically feasible.
Great, thank you so much, Philippe. So let's move on to another question. Another anonymous attendee has asked, do you need to consider the material in the design process?
Okay, so maybe I'll take this one. Of course, if you will have something to add, Philippe and Krzysztof, please don't worry about it and add. Of course, you should. There are different specifics of the materials that has to be considered when you are still in the process of designing the material, of designing the application. You can do it two ways. You can either choose a material that will work for the application that you already designed, or you can consider the material through the design process. We have, I believe, one of the examples. If you are designing something with a small part that have small parts or fine detail, and you are using very high temperature printing material, this is a very, very short way to have troubles, because there won't be enough time for the material, for the temperature to get out of the place where the material is being built up in this one small place. So there are some requirements that you should follow if you can consider choosing the material before designing the part. Still, unfortunately, most of the time people are considering material after choosing the design or after designing the part, or even worse, they are taking the design that was created for CNC machines and they are trying to 3D print it. That's not a good result. But this one, the design for additive manufacturing, so DFAM, is the very, very interesting topic that I believe we should also cover in the future. I believe you wanted to add something?
Yeah, that's actually a brilliant point. I mean, design for additive manufacturing is key. I mean, this is the first thought that really should spring to mind when thinking about 3D printing anything. You know, try and optimize your design for 3D printing. And of course, material comes close second. If you know exactly what the function of the part would be, try and incorporate it into the design with the material specification in mind. And it actually depends if you're working on a end use part, because then you might be limited in what you're allowed to do. But when you're doing an iterative design, or you are making a functional prototype, this is a brilliant point to consider all the positive aspects that can arise from a proper material choice. Like, let's say, oil resistance. Maybe your application calls for some kind of chemical resistance, and sourcing a material, properly would actually benefit you greatly.
I think that we can just add one thing, that thanks to dual head printers and dual head modules, we have slightly more freedom with the design. So as Philip mentioned, sometimes there are the applications that cannot be changed, and there are the parts that cannot be changed. And thanks to the Solvo support or the advanced support solutions, we are able to produce the more complex geometries.
Right. Thank you, gentlemen. We do have a few more material questions. The first one is, what are the application differences between PA6 and PA12GF materials?
Philip, for you.
Yeah,
it was PA12 and PAGF, right?
No, PA6GF.
Okay.
Right?
Yeah,
okay. Well, PA6 and PA12 are based on different monomers. They're both what we would call, nylon, but this is really not saying much. It is a specific family of materials. Overall, they share some similarities, but they also differ in rigidity, toughness, tensile strength, elongation. They will display some differences. They are fairly robust when it comes to chemical resistance, but by far the biggest differentiating factor mentioned is glass fiber loading. A glass fiber loaded material will be abrasive because of the fibers inside, but it also will be significantly more rigid. It will display a higher tensile strength. It will be less flexible. It will be able to withstand higher working temperatures and higher loads. But it actually depends on the application again. PA6 glass fiber reinforced is actually very widely adopted in the industry. I do believe that a lot of different electric tools and closures are actually made of PA glass fiber reinforced, but it also depends on how much fiber load you actually have in the material. If you have, let's say, 7, 5, or maybe even 10%, you will only get some amount of the difference that the fiber actually can make. But the industrial grade loading goes to 30% and possibly even more. and this will greatly affect the performance and the overall characteristics of the material. So that's a very broad question, but hopefully I just scratched the surface there.
Thank you very much. Another question from Isabel this time. What can happen if the material is stored improperly?
Okay, this was the part of Krzysztof's presentation, so maybe you may start, and I with Philip will cover something if there will be anything to add.
Okay, definitely the material handling and preparation of the material before printing is a very important topic. And what can happen, it can not only visual quality, as you saw on the slide before, the part looks very messy, let's say, but it's about the layer adhesion and the mechanical properties of the part. The improper material preparation before printing and handling during the printing process, so not storing in the heated chamber, heated dry chamber during the printing process, can also lead to the clog of the nozzle that can lead to the failed print. So preparing the material before printing is one of the most important things that we are working with our clients and our users.
Great. Another question from Anna Paula this time. Can thermoplastic polyester be used in FDM printers?
Well, the overall question is yes. I do believe that polyethylene terephthalate or PET is chemically a polyester. So, well, and it's a fairly commonly used material. So, yeah, the answer is yes, it can be.
Okay. Next question, still about materials, is PLA biodegradable under normal conditions?
That's a great question, and it comes with so many different angles. Okay, PLA by itself is biodegradable, and the normal conditions. I'm not exactly sure what the person asking the question meant by that, but you know, if you put a PLA part in a compost bin, it will degrade away eventually. But actually there are plasticizers and additives in pretty much all 3D printing filaments, and PLA also uses some of those materials. And as far as the polylactic structure will degrade away, those substances will also be released, and they're not necessarily the best of substances. They're not harmful in any way when bounded together, but as the degradation goes on, they will be released. So you can consider PLA biodegradable, but should you toss your PLA prints on the compost bin, maybe try not to.
Okay, great. So we should start wrapping up, but I think we can still fit a couple of questions in. One question about the new printer is the F350 filtration system a built-in component of the printer itself, or is it a separate add-on?
Okay, so generally speaking, it's an add-on, and this is something that the user should need. Not all materials are harmful, so not all printing materials should be needed industrial grade air filtration system. Also, this is a part that when we are talking about air filtration, there are some things that you have to exchange inside. So we decided to give a free choice to our users, so they can tell us if they will need an industrial grade air filtration system or not. There is also one reason that we did this. There are many of our users that already has industrial grade air filtration systems in their facilities. So there is not always a need to place one in the printer when there is one in the place where the printer will be installed.
And maybe the last question, we'll see if we have time. What are the main differences between PEEK and PEC, the high performance polymers?
It's Philip's favorite question.
Yeah, again, it very strongly depends on the application again. The main difference, Okay, the chemical structure is different because actually PEEK stands for polyether ketone, polyether ether ketone, and PEG for polyether ketone ketone, but they actually are part of the same group, commonly referred to as PEG, but they do display different behavior. So PEG overall would crystallize somewhat more slowly, and most applications do not call for a strictly recrystallized part, while PEEK actually is more sought after if it's in its higher crystallinity. Well, yeah, that's one difference. But you know, the material properties vary. I mean, tensile strength is different. It depends on how the material is printed, because you can print it amorphous, you can then recrystallize it. Chemical resistance is sort of similar. There are some thermal differences. For instance, you know, PEEK has a glass transition temperature of around 140 degrees, while PEG is slightly more resistant at 156, I do believe. Well, again, depending on the grade. There are significant differences that can make or break an application, but very, you know, defining difference other than just, you know, chemistry and applications is hard to pinpoint, really.
Okay, well, I see that we are now at 5. I remind all participants that if you do have a question that hasn't been answered, you can contact the email on the screen, especially about the printers. On that note, I will say thank you all for attending today. Thank you to our panelists. It was a fantastic presentation. I hope you all enjoyed it. Don't forget that the webinar video will be uploaded on 3Dnatives YouTube channel if you would like to watch it again, or if you would like to share it with friends or anyone you'd like. Thank you again and have a great day.
Thank you, Mehdi. Thanks everyone for attending, and I hope you learned a lot today.
Yeah, thank you very much. Actually, I'm looking forward to continuing, because I think it's a great job that we started covering those materials. It's really an underplayed and yet so important topic. And so thank you.
Thank you. Have a great afternoon. Looking to speak to you more often. Bye.
Thank you. Thank you all. I will end it there, but have a fantastic day, panelists. Have a fantastic day, attendees. Goodbye.
Bye.
Bye.